Gravity or gravitation is a natural phenomenon by which all things with energy are brought towards one another, including stars, planets, galaxies and even light and subatomic particles. Gravity is responsible for the complexity in the universe by creating spheres of hydrogen, where hydrogen fuses under pressure to form stars, and grouping them into galaxies. Without gravity, the universe would be an uncomplicated one, existing without thermal energy and composed only of equally spaced particles. On Earth, gravity gives weight to physical objects and causes the tides. Gravity has an infinite range, although its effects become increasingly weaker on farther objects. Gravity is most accurately described by the general theory of relativity, which describes gravity, not as a force, but as a consequence of the curvature of space-time caused by the uneven distribution of mass, energy, and resulting in time dilation, where time lapses more slowly in strong gravitation. However, for most applications, gravity is well approximated by Newton's law of universal gravitation, which postulates that gravity is a force where two bodies of mass are directly drawn to each other according to a mathematical relationship, where the attractive force is proportional to the product of their masses and inversely proportional to the square of the distance between them. This is considered to occur over an infinite range, such that all bodies in the universe are drawn to each other no matter how far they are apart. Gravity is the weakest of the four fundamental interactions of nature. The gravitational attraction is approximately 10⁻38 times the strength of the strong force, 10⁻36 times the strength of the electromagnetic force, and 10⁻29 times the strength of the weak force. As a consequence, gravity has a negligible influence on the behavior of subatomic particles, and plays no role in determining the internal properties of everyday matter. On the other hand, gravity is the dominant interaction at the macroscopic scale, and is the cause of the formation, shape, and trajectory of astronomical bodies. It is responsible for various phenomena observed on Earth and throughout the universe. For example, it causes the Earth and the other planets to orbit the Sun, the Moon to orbit the Earth, the formation of tides, and the formation and evolution of galaxies, stars in the solar system. In pursuit of a theory of everything, the merging of general relativity and quantum mechanics into a more general theory of quantum gravity has become an area of research. History of gravitational theory. Scientific revolution. Modern work on gravitational theory began with the work of Galileo Galilei in the late 16th and early 17th centuries. In his famous experiment dropping balls from the Tower of Pisa, and later with careful measurements of balls rolling down inclines, Galileo showed that gravity accelerates all objects at the same rate. This was a major departure from Aristotle's belief that heavier objects accelerate faster. Galileo postulated air resistance as the reason that lighter objects may fall more slowly in an atmosphere. Galileo's work set the stage for the formulation of Newton's theory of gravity. Newton's theory of gravitation. In 1687, English mathematician Sir Isaac Newton published Principia, which hypothesizes the inverse square law of universal gravitation. In his own words, I deduced that the forces which keep the planets in their orbs must be, reciprocally as the squares of their distances from the centers about which they revolve, and thereby compared the force requisite to keep the Moon in her orb with the force of gravity at the surface of the Earth, and found them answer pretty nearly. The equation is the following, where F is the force, m1 and m2 are the masses of the objects interacting, r is the distance between the centers of the masses, and g is the gravitational constant. Newton's theory enjoyed its greatest success when it was used to predict the existence of Neptune based on motions of Uranus that could not be accounted for by the actions of the other planets. Calculations by both John Couch Adams and Urbain Le Verrier predicted the general position of the planet, and Le Verrier's calculations are what led Johann Gottfried Gall to the discovery of Neptune. A discrepancy in Mercury's orbit pointed out flaws in Newton's theory. By the end of the 19th century, it was known that it saw but showed slight perturbations that could not be accounted for entirely under Newton's theory. But all searches for another perturbing body had been fruitless. The issue was resolved in 1915 by Albert Einstein's new theory of general relativity, which accounted for the small discrepancy in Mercury's orbit. Although Newton's theory has been superseded by Einstein's general relativity, most modern non-relativistic gravitational calculations are still made using the Newton's theory because it is simpler to work with and it gives sufficiently accurate results for most applications involving sufficiently small masses, speeds and energies. Equivalence principle. The equivalence principle, explored by a succession of researchers including Galileo, Lorentz, Tvos, and Einstein, expresses the idea that all objects fall in the same way. The simplest way to test the weak equivalence principle is to drop two objects of different masses or compositions in a vacuum and see whether they hit the ground at the same time. Such experiments demonstrate that all objects fall at the same rate when other forces are negligible. More sophisticated tests use a torsion balance of a type invented by Tvos. Satellite experiments, for example STEP, are planned for more accurate experiments in space. Formulations of the equivalence principle include the weak equivalence principle. The trajectory of a point mass in a gravitational field depends only on its initial position and velocity, and is independent of its composition. The Einsteinian equivalence principle. The outcome of any local non-gravitational experiment in a freely falling laboratory is independent of the velocity of the laboratory and its location in spacetime. The strong equivalence principle requiring both of the above. General relativity. In general relativity, the effects of gravitation are ascribed to spacetime curvature instead of a force. The starting point for general relativity is the equivalence principle, which equates freefall with inertial motion and describes free-falling inertial objects as being accelerated relative to non-inertial observers on the ground. In Newtonian physics, however, no such acceleration can occur unless at least one of the objects is being operated on by a force. Einstein proposed that spacetime is curved by matter, and that free-falling objects are moving along locally straight paths in curved spacetime. These straight paths are called geodesics. Like Newton's first law of motion, Einstein's theory states that if a force is applied on an object, it would deviate from a geodesic. For instance, we are no longer following geodesics while standing because the mechanical resistance of the Earth exerts an upward force on us, and we are non-inertial on the ground as a result. This explains why moving along the geodesics in spacetime is considered inertial. Einstein discovered the field equations of general relativity, which relate the presence of matter and the curvature of spacetime and are named after him. The Einstein field equations are a set of 10 simultaneous, nonlinear, differential equations. The solutions of the field equations are the components of the metric tensor of spacetime. A metric tensor describes a geometry of spacetime. The geodesic paths for a spacetime are calculated from the metric tensor. Solutions. Notable solutions of the Einstein field equations include the Schwarzschild solution, which describes spacetime surrounding a spherically symmetric non-rotating uncharged massive object. For compact enough objects, this solution generated a black hole with a central singularity. For radial distances from the center which are much greater than the Schwarzschild radius, the accelerations predicted by the Schwarzschild solution are practically identical to those predicted by Newton's theory of gravity. The Reissner-Nordström solution, in which the central object has an electrical charge. For charges with a geometrized length which are less than the geometrized length of the mass of the object, this solution produces black holes with two event horizons. The Kerr solution for rotating massive objects. This solution also produces black holes with multiple event horizons. The Kerr-Newman solution for charged, rotating massive objects. This solution also produces black holes with multiple event horizons. The cosmological Friedmann-Lemaitre-Robertson-Walker solution, which predicts the expansion of the universe. The tests of general relativity included the following. General relativity accounts for the anomalous perihelion precession of Mercury. The prediction that time runs slower at lower potentials has been confirmed by the Pound-Rebka experiment, the Haffler-Keating experiment, and the GPS. The prediction of the deflection of light was first confirmed by Arthur Stanley Eddington from his observations during the solar eclipse of May 29, 1919. Eddington measured starlight deflections twice those predicted by Newtonian corpuscular theory, in accordance with the predictions of general relativity. However, his interpretation of the results was later disputed. More recent tests using radio interferometric measurements of quasars passing behind the Sun have more accurately and consistently confirmed the deflection of light to the degree predicted by general relativity. See also gravitational lens. The time delay of light passing close to a massive object was first identified by Erwin I. Shapiro in 1964 in interplanetary spacecraft signals. Gravitational radiation has been indirectly confirmed through studies of binary pulsars. Alexander Friedmann in 1922 found that Einstein equations have non-stationary solutions. In 1927, Georges Lemaitre showed that static solutions of the Einstein equations, which are possible in the presence of the cosmological constant, are unstable, and therefore the static universe envisioned by Einstein could not exist. Later, in 1931, Einstein himself agreed with the results of Friedmann and Lemaitre. Thus, general relativity predicted that the universe had to be non-static, it had to either expand or contract. The expansion of the universe discovered by Edwin Hubble in 1929 confirmed this prediction. The theory's prediction of frame dragging was consistent with the recent gravity probe B results. General relativity predicts that light should lose its energy when traveling away from massive bodies through gravitational redshift. This was verified on Earth and in the Solar System around 1960. Gravity and quantum mechanics. In the decades after the discovery of general relativity, it was realized that general relativity is incompatible with quantum mechanics. It is possible to describe gravity in the framework of quantum field theory like the other fundamental forces, such that the attractive force of gravity arises due to exchange of virtual gravitons, in the same way as the electromagnetic force arises from exchange of virtual photons. This reproduces general relativity in the classical limit. However, this approach fails at short distances of the order of the Planck length, where a more complete theory of quantum gravity is required. Specifics: Earth's gravity. Every planetary body is surrounded by its own gravitational field, which can be conceptualized with Newtonian physics as exerting an attractive force on all objects. Assuming a spherically symmetrical planet, the strength of this field at any given point above the surface is proportional to the planetary body's mass and inversely proportional to the square of the distance from the center of the body. The strength of the gravitational field is numerically equal to the acceleration of objects under its influence. The rate of acceleration of falling objects near the Earth's surface varies very slightly depending on latitude, surface features such as mountains and ridges, and perhaps unusually high or low subsurface densities. For purposes of weight and measures, a standard gravity value is defined by the International Bureau of Weight and Measures. Under the International System of Units, that value, denoted G, is G equals 9.80665 meters per square second. The standard value of 9.80665 meters per square second is the one originally adopted by the International Committee on Weights and Measures in 1901 for 45 degrees latitude, even though it has been shown to be too high by about 5 parts in 10,000. This value has persisted in meteorology and in some standard atmospheres as the value for 45 degrees latitude, even though it applies more precisely to latitude of 45 degrees 32 minutes 33 seconds. Assuming the standardized value for g and ignoring air resistance. This means that an object falling freely near the Earth's surface increases its velocity by 9.80665 meters per second for each second of its descent. Thus, an object starting from rest will attain a velocity of 9.80665 meters per second after 1 second, approximately 19.62 meters per second after 2 seconds, and so on, adding 9.80665 meters per second to each resulting velocity. Also, again ignoring air resistance, any and all objects, when dropped from the same height, will hit the ground at the same time. According to Newton's third law, the Earth itself experiences a force equal in magnitude and opposite in direction to that which it exerts on a falling object. This means that the Earth also accelerates towards the object until they collide. Because the mass of the Earth is huge, however, the acceleration imparted to the Earth by this opposite force is negligible in comparison to the objects. If the object doesn't bounce after it has collided with the Earth, each of them then exerts a repulsive contact force on the other which effectively balances the attractive force of gravity and prevents further acceleration. The force of gravity on Earth is the resultant of two forces. The gravitational attraction in accordance with Newton's universal law of gravitation, and the centrifugal force, which results from the choice of an earth-bound, rotating frame of reference. At the equator, the force of gravity is the weakest due to the centrifugal force caused by the Earth's rotation. The force of gravity varies with latitude and increases from about 9.780 meters per square second at the equator to about 9.832 meters per square second at the poles. Equations for a falling body near the surface of the Earth under an assumption of constant gravitational attraction. Newton's law of universal gravitation simplifies to F equals mg, where m is the mass of the body and g is a constant vector with an average magnitude of 9.81 meters per square second on Earth. This resulting force is the object's weight. The acceleration due to gravity is equal to this g. An initially stationary object which is allowed to fall freely under gravity drops a distance which is proportional to the square of the elapsed time. The image on the right, spanning half a second, was captured with a stroboscopic flash at 20 flashes per second. During the first 1/20th of a second the ball drops 1 unit of distance, by 2/20ths it has dropped it total of 4 units, by 3/20ths, 9 units, and so on. Under the same constant gravity assumptions, the potential energy, EP, of a body at height h is given by EP equals mgh. This expression is valid only over small distances h from the surface of the Earth. Similarly, the expression for the maximum height reached by a vertically projected body with initial velocity v is useful for small heights and small initial velocities only. Gravity and astronomy. The application of Newton's law of gravity has enabled the acquisition of much of the detailed information we have about the planets in the solar system, the mass of the Sun, and details of quasars. Even the existence of dark matter is inferred using Newton's law of gravity. Although we have not traveled to all the planets nor to the Sun, we know their masses. These masses are obtained by applying the laws of gravity to the measured characteristics of the orbit. In space, an object maintains its orbit because of the force of gravity acting upon it. Planets orbit stars, stars orbit galactic centers, galaxies orbit a center of mass in clusters, and clusters orbit in superclusters. The force of gravity exerted on one object by another is directly proportional to the product of those objects' masses and inversely proportional to the square of the distance between them. Gravitational radiation. In general relativity, gravitational radiation is generated in situations where the curvature of space-time is oscillating, such as is the case with co-orbiting objects. The gravitational radiation emitted by the solar system is far too small to measure. However, gravitational radiation has been indirectly observed as an energy loss over time in binary pulsar systems such as PSR B1913+16. It is believed that neutron star mergers and black hole formation may create detectable amounts of gravitational radiation. Gravitational radiation observatories such as the Laser Interferometer Gravitational Wave Observatory have been created to study the problem. No confirmed detections have been made of this hypothetical radiation. Speed of gravity. In December 2012, a research team in China announced that it had produced measurements of the phase lag of Earth tides during full and new moons, which seem to prove that the speed of gravity is equal to the speed of light. This means that if the Sun suddenly disappeared, the Earth would keep orbiting it normally for 8 minutes, which is the time light takes to travel that distance. The team's findings were released in the Chinese Science Bulletin in February 2013.